All right, so we're going to continue talking about precipitation today, and the homework assignment that you've got related to precipitation is due a week from today. So you can get started on that assignment after some of the things that we go over in today's class, but we probably will continue the topic on Tuesday, so we may not get through everything that's covered on that assignment by the end of today. You can definitely get started. You've already seen intensity, duration, frequency curves, or at least you've seen a representation of one of the curves on some of the examples and on the homework that you did related to time of concentration. Often these curves are expressed in terms of intensity. Sometimes they're expressed in terms of depth. And so if they're expressed in terms of depth, then the characteristic shape is more tapering downward rather than tapering with the shape that's shown there. So here it's intensity, and this one is inches per hour, and it's expressed logarithmically, because if it's not expressed logarithmically, then you tend not to be able to show the really rare 100-year storm intensities on the same figure as a storm that has a return period of only 2 years. And if we're going out to the duration of the storm, you can see that the intensity is as low as 1/10 of an inch per hour. So the only way to display all that was with the logarithmic scale. So IDF stands for intensity, duration, frequency. So if you want to find the depth of a certain storm, what you would do is you would multiply the intensity by the duration. So a storm that is a 2-year return period just means that in any given year, there's a 50% chance that you'd see that storm. But in any given year, there's also a 20% chance of having a 5-year storm. So these probabilities are, in a sense, cumulative, that just because you had a 2-year storm doesn't mean you're not going to have another one in the same year. And it also, you're exposed to the risk of all of these storms in any given year. But if we wanted to find the depth that occurred during a storm that has a duration of 1 hour, what we could do is we could go up to the 2-year and then follow it over. That's 0.9 inches per hour. So 0.9 inches per hour for 1 hour would mean that the overall depth was 0.9. So just be aware of when we go to a website that shows these IDF curves, you can click on a map. It will generate it either in terms of intensity or in terms of depth. Yeah?
Is there a way to plot those grids in Excel? I know you can do logarithmic axes, but I don't know if you can get the line to show in Excel.
Yeah, I think so. If we have some time at the end of class, let's go through and do that, because we are going to be creating, doing IDF calculations, but I've never graphed it as part of the example before. But if we've got the time, let's give it a shot. All right, so where does this data come from? Well, it comes from observations. Like, you can go onto websites where they've been posting the data from those rain gauges. And remember, I showed you yesterday, Tuesday, a map of where there's some rain gauges in the area here. Most of those rain gauges have between 10 and 30 years worth of data. Some of them have data all the way back into the 50s, though. And so you take all the data that you get, and the formula for calculating the return period, so 2-year, 5-year, 10-year, that return period is calculated based on the number of years of data that you have, and then you're ranking a certain observation from highest to lowest. So let's say we have a spreadsheet table with just year after year of data, and it's all been recorded for the same duration. So you would order the data, use this formula to calculate the return period, and then you do the same thing for other rainfall durations. And so just as an illustration of that and how we go through the process of interpolating, let's say that we had observations of rainfall. It looks like these are depths rather than intensity. So we have just so far sorted from highest to smallest. And so at the top of the list is there was this observation where in 5 minutes there was 12.1, and that would be a lot of inches for 5 minutes. That might be millimeters. In the second place, 11. So to calculate the return period, what you'd say is if we had a total of 32 years worth of data that this came from, and so not shown is 4 through 32. All of the top storms for those years, we ranked from largest to smallest. So the return period, what we've seen is during the 32 years, the number one storm that we had was this one where for a 5-minute duration was 12.1 millimeters. So what that means is that the return period for that particular storm is every 33 years. But the next one, we're doing n plus 1 divided by m. And since m is 2 for the second place storm, that means the return period of the second place storm of 11 millimeters is every 16.5 years. If we go back to the IDF table, there wasn't a curve that had 33 or 16.5. It's more customary to express it in 2, 5, 10, 25, 50, and so on. So when you naturally have data that lines up to these weird return periods, you're going to have to interpolate to find out what's the 25-year storm. So you would use a linear interpolation to be able to say what's the 25-year storm depth. And so we would say, find the slope between 33 and 16.5, and likewise between 12.1 and 11.0, and just linearly interpolate. And so that's what this next step in the illustration is saying, that we've calculated the return period. So now we have to do it for all of the durations and linear interpolate. So we generate for the 20-year storm. If we wanted to know the 20-year storm, then we would go, it's somewhere between 11 and 12.1, and it's closer to, 16.5 is closer to 20 than 33 is, and so it's going to be just a little bit more than 11. So we go through the linear interpolation process, and we are going to be, in the homework, going to find some actual rain gauge data, and you're going to go through this process of downloading a spreadsheet file, ordering it, calculating the return period, and interpolating. But you'll only be able to do it, if I remember correctly, for the 24-hour data, because what we have from the data that's available is daily totals. It's actually pretty rare to have rainfall, depth, or intensity data for anything other than daily totals. I mean, at a handful of airports and some research stations, they might have it in 15-minute increments. But that's pretty specialized, uncommon data. So for the assignment, what we'll do is we won't have lots of different columns corresponding to different rainfall durations, but you will have lots of rows. Each one of the rows is going to refer to some storm incident that we actually observe, and then you're going to use that to calculate the return period. So I'll give you an illustration of basically how to head down that road once we download some data from an actual station today in class. So there's a lot of different places online you can get good rainfall data besides just like WSAZ. Prism is an interesting website that's operated by Oregon State, and they have done that with a grant from the Department of Agriculture. And the thing that's nice about Prism is they look long-term data. Instead of focusing on individual storms, they're coming up with monthly totals, annual totals, and what's, I think, pretty interesting is annual averages. And so they have a variety of maps where you can look and see on a 30-year basis what's the annual precipitation average. So you can see here in West Virginia where we are, we're in the range of about, let's see, based on the color there, about 40 inches per year. In the mountains, they get more. But of course, out in the west, it's typically more dry, and there are some spots in the west where they're seeing less than 4 inches per year of rain. The Gulf Coast gets a lot of precipitation, and the most is along the Pacific Northwest. So we all know it rains in Seattle, and here's the visual proof of that. So that's just one illustration of the data that's available on this PRISM website. I've used it in the past for the historical data. Like you can look up what was the annual average, what was the annual rainfall in a certain year. Like if you wanted to see what was the climate like in 1983. And that was a really wet year that caused a lot of flooding out in the western United States. So PRISM is kind of a top-level view of the historical data. Precipitation Frequency Data Server is something you're going to use a lot. Of all the tools I'm showing you today, it's probably the most useful in terms of hydraulic design because what it allows you to do is pick a spot on the map and it'll tell you an IDF table for it. And it's nice because it's already got all of the statistics done in the background. It's validated, it's accepted, it's defensible, so that if, you know, in engineering a lot of times the question is, why did you do that? Like, what are your assumptions? You know, if somebody doesn't like the result of your analysis, they're going to start throwing stones and questioning the data that you used, questioning your methods. And this is as defensible as it gets. This is the gold standard of how much the rainfall is going to be in a certain area. So you can click on the map or choose a state. So if we click here on West Virginia, it zooms in on the map a bit. And up here at the top, we first of all can choose between whether we want to create a table that is depth or intensity. So we can have an intensity chart if we're going to be doing something like the rational method, Q equals CIA. And if we need an I, then we would choose to generate a table of intensities. But if we want to know, like maybe pond volume sizing, and we maybe would want instead to know the depths, or if we're interested in things like soil science or crops, those are applications that maybe depth would be more important as well. Of course, you can switch between units. Now this time series data, this is a complicated distinction. There's partial duration and annual maximum. An annual maximum, the theory there, if we go back to the example where we're saying, well, let's make our own IDF table. We have 32 years of data. There's two ways we could have sorted the data. One is for every year, we could have picked out the biggest storm for that particular year and then ranked them once we picked out the biggest in every year. Or we could have picked the top 32 regardless of which year it was in. So some years are going to have like two really big storms, and if we were using the annual maximum approach, we would only see the biggest of those two storms. But the partial duration approach up here, partial duration is saying we're not going to limit ourselves to considering only the largest storm from any given year. Partial duration is the most common, but there are some cases where by code or by convention they're using annual maximum instead. It doesn't have a huge effect on the IDF table in most spots. Okay, so let's just create one for intensity using English units and the more standard partial duration. What you can do is you can type in the latitude and longitude, or you can type in an address and it will move the cursor to wherever you want it. Or you can just drag and drop the target. So let's see, where's the tri-state? I guess it's around here somewhere. We could zoom in a little more, find Huntington. All right, let's drop it right on Marshall. Okay, so what is the precipitation situation like here in Huntington? So below that now, it's created a table. We have each column represents the return periods, and each row is representing the storm duration. So that's a little bit different. Sometimes the X and Y for the table is reversed. But what we could see is if our analysis told us that we need to find the runoff for a 10-year storm in Huntington, you know, we're sizing a catch basin for a parking lot and we know the area the intensity for that storm. If we have calculated the time of concentration, looked at the travel time across that parking lot, maybe it's 15 minutes. So we say 10-year storm, 15-minute duration, the intensity will be 4.31 inches per hour. So here at the top it's told us the units, inches per hour. Now there's also a range beneath that. And that range is related to the confidence interval. So 4.34 is in the middle of that range, but we're 90% confident that the actual 10-year return period, 15-minute storm duration intensity is between 3.95 and 4.71. So if you want to have 90% confidence that you used the right intensity, then you want to be conservative, then you'd use the highest of that range. You'd use 4.71. So by using 4.71, now there's only a 10% chance that actually the rainfall amount is higher than what you picked. And likewise here, this lower range here, if you wanted to see like what's the potential that you've oversized your network and it's actually excessively too much capacity in the pipe, use the lower of the range and see how is the pipe performing at the lower of the 90% confidence interval. And outside of that, there's a 10% chance that the actual precipitation value isn't inside of that range. So most of the time when you're doing analysis, you might run the numbers just at the low and the high end to see what's happening, but the middle value is what people usually concern themselves with. Even in a research setting, sometimes people will roll their eyes if you do the analysis at both ends of the confidence interval as well as just the given intensity. So that is what it looks like if you do precipitation intensity. Here I'll show you for depth. If we do depth, I'm not sure if it automatically updated. So how do we know that these are depths rather than intensities? Even if we didn't know what we clicked on at the top, just the numbers themselves tell you whether it's an intensity or a depth. So what's the clue? Yeah, the units, inches, that's a pretty good clue. The other clue is look at duration. Okay, 5, 10, 15, 30. The amount is getting bigger as the duration increases. If it's an intensity, that number is going to be getting smaller. So let's switch back to intensity. Okay, so if it's intensity, 4, 3, 2, 1, it's getting smaller because as the storm duration gets longer, it can't keep up that same intensity for a really long time period. You can only have high intensity for a short period. So if you look at the data table and the number is getting smaller with increasing time, you're looking at intensity, or you can check the units. But in the case of depths, the amounts are getting bigger because although the intensity is going down, the cumulative depth is larger. Because you've got, in a 60-minute storm, you've got the 5-minute amount, you've also got the 10-minute amount, and so on. So you had a longer period for that rainfall to accumulate. Okay, so the precipitation data frequency server is pretty nice. You can have it create a graph, an IDF curve graph for you. Here's how it looks if we're doing it in terms of duration. Here's how it looks if we're doing it in terms of intensity. Now here, they've done it log on the time axis and also on the amount axis. I don't usually bother with their graphical. I would just create my own in Excel using the numbers. You can copy those numbers over to Excel and paste them. Looks like you can also get it in a table format where they'll serve you up the file. Let's see, it comes up in Excel. Yeah, all right. So there's our IDF table. Gives you the latitude, the longitude, the elevation of the point that you clicked on. Now, how did it get this? Like, where did this data come from? Well, what they did was they looked at all of the rain gauge data in the area, and they extrapolated. They weighted with more emphasis on the stations that have a longer history, and less emphasis for those stations that have a short history. And then they looked at general trends as well. It's not just if there were 3 gauges in the area, they don't just strictly rely on those 3 gauges in the area. They also know, based on your geography, what kind of typical rainfall patterns there exist. And I'll show you a map that illustrates in the United States these different types of rainfall that we've got. Before we do that, though, let's look at this last source of data, the National Climate Data Center. This is where you can actually download the data for an individual station. So in the homework, I'm going to ask you to go get the data for an individual station. And the way you do that is, let's click first on Data Tools, and then, what is it? Find a station or select a location? Find a station, then daily summaries. Okay, so find a station. It's already set to daily summaries. Let's kind of zoom in a little bit on some spots that we maybe would be interested in and see where are the stations that we can choose from. All right. Which stations it shows is going to adjust based on the date range that you've selected. And so right now, we just have a single day worth of data. And so for some reason, when you do that, it doesn't show the Huntington or the Charleston airport. But I think it might take a couple of days before Huntington and Charleston airport data shows up, because that data is validated before it's posted, I think. But if we go back and say, well, we want some place that has data from, we're interested in 1976 until September 1st. Okay, 1976. September 1st, 76 until September 1st, 2018, apply. So now we've got a date range. And actually, there's more stations now that we've gone back a couple of days. And we want to make sure that that station has precipitation data available. So it'll filter that. If we were asking for data that wasn't available, like evaporation data, that's pretty uncommon. There's only a handful of stations that are reporting that. So we won't filter it by that. But now, if we click, there's the airport. So you click on the locations and it tells you the name, and they have a serial number, the lat long. You know, we could find the Charleston airport. There's Charleston Yeager. So from 47 until 2018 with 100% coverage. They haven't missed a single day at that airport. They've had no equipment failures. Some of these stations, though, will only have 63% coverage. Now, this is pretty awesome. The data goes back in Hamlin to 1899. So they probably didn't have a tipping bucket in Hamlin back in 1899. It was some guy in overalls and a ruler, right? But so let's just get the Huntington Airport. We'll add it to the cart. And what you have to do is tell it your email address, and it'll email you when it's ready to download, because it takes a while for it to process that. We don't want a PDF. A PDF is just a picture of the data. We want the real data. So we'll take it as a CSV. That will allow us to download it in Excel. So from 76 to 2018, we'll continue here, and it'll ask us which data fields we want. So we want the name. Yes, we could go for the lat long. These data flags, if there's missing data, or if the equipment is screwy, or if they have any other kind of note, then it will include certain flags. And there's a table of contents you can get from the NCDC that'll tell you what those flags mean. But for a station like the airport, they've already quality checked and fixed any errors in the data. So I don't usually worry about the data flags. But let's just have it include the precipitation. You can have a lot of other stuff too. You can have it tell you the air temperature and like if it was sunny and whatnot. And some of that stuff's kind of interesting, but it's just the precipitation we'll go for in this time. So we click continue, and then it asks for the email address. And let's see how long it takes to generate this. I've had some cases where the students had to wait a whole day to get the order, and it might have been that the servers were slowed down for some reason. And sometimes it may be immediately available. So let's see, queued. The status is queued. So let's check again. Processing. Oh, I like the sound of that. Check again. It shouldn't take long. A watch pot never boils. All right, one last time before we move on. Processing, come on. It's not that big of an order. All right, I guess you get what you pay for. We'll come back to this in a minute. So the data we're downloading is from the airport. Here's some data from the airport. A couple of years ago, I was running a rain gauge out in a watershed in Ona, which was about 20 miles from the airport. And what I did was I graphed the rain gauge in Ona compared to the rain gauge at the airport. So 20 miles apart, you'd think they're going to get about the same precipitation in both spots. And there definitely is a correlation. I mean, you can see that when there's a wet day at the airport, there's usually a wet day in Ona. And these graphs cross each other a couple of times. But then there's also some divergence. Towards the end especially, so we're looking at August and September, there was a lot more wet weather at the airport than there was in Ona. So the point that I am making here is something called spatial distribution. And that's just a funny word that says the amounts of things over space, like how much is there over here, how much is there over there. And so whenever you're doing an analysis, it would potentially be a mistake to just take the rainfall data from the airport and say the rainfall at the airport describes what you can expect to see in Milton. You know, like maybe over a 30-year average, probably they're pretty close. But on a given day, there could be substantial variation. When we're gathering rainfall data, you'll notice that this rain gauge is placed in an open area out of the way of buildings or vegetation that could cause interception. So those obstructions can reduce the intensity of the rainfall. So usually the rain gauges are put out in an open area, and also they're off the ground a bit. This figure doesn't show that very well, but if the rain gauge is too close to the surface of the ground and it's raining really hard, sometimes the rain bounces from the ground back into the rain gauge. Splashes. So if there's a puddle on the ground, the splashes could get into the rain gauge in addition to the stuff that's coming straight into the rain gauge from above. So that in-splashing needs to be avoided. It's possible that there can be evaporation from the rain gauge before it's measured, and especially if it's just a daily total where somebody's going out to visually inspect at each day the same time. There could be evaporation if there was a rain shower in the morning and then a sunny afternoon, and then the person who's just a volunteer rain enthusiast checks at 7 p.m. It could have rained more than they observe. And so the tipping bucket gets away from that problem. But there still can be instrument errors where the machines need to be calibrated. Scum can accumulate on the little cups that holds water. And so if you have a slime layer or some organic sediment that's inside of that little tipping bucket cup, then that can reduce the volume that it holds, and then it would be tipping too often. Low intensity precipitation sometimes isn't enough to actually trigger any kind of tip, like it can evaporate before it is measured. And occult precipitation, honestly, I don't remember what that means. Occult, that means like satanic, right? But I don't think that's what that means in this case. We're going to have to consult Google on this one. Occult. Occult precipitation. Does it mean at night? The ability of vegetation to precipitate the small water droplets existing in fog. Okay. I guess that means that you aren't going to have the same mist isn't going to accumulate on a rain gauge necessarily in the same way that vegetation can draw it out of the air. So how much rainfall plants are getting isn't always the same as how much rainfall this metal container is receiving. Because in the same way that plants can evapotranspirate, like they can exhale water vapor, they can also draw in water vapor. So we all learned something new today, occult precipitation. I reminded myself what that was. I'm sure at one point I knew it and forgot it. All right, so this is just a little representation that shows how you could calculate what is the average precipitation amount inside of a watershed. Remember yesterday, Tuesday in class, what we did was using Google Earth, we turned on the terrain, which is kind of like a 3D elevation model that the image is draped over. And then by pivoting around, by changing our view of the terrain from kind of like an isometric 3D perspective, we were able to visualize where were the ridge lines. And so that's what this black line is meant to represent, is you've got some sort of a ridge line that's defined by high points in the topography, and this is our watershed of interest. What if we have a lot of different rain gauges inside and surrounding that watershed? So just a simple aerial average only takes into account the rain gauges that are inside of the watershed, and it ignores those on the outside. So we're going to look at different ways of calculating an average. This is the simplest of them. Just they all have equal weight, and we are including the ones that are relatively close to the border. So that equal weighting, what it doesn't do is it doesn't give more emphasis to the ones that are on the inside rather than the outside. And so the Thiessen method is a way of assigning areas, contributing areas based on the rain gauge. And so what you would do is you would connect the dots between two different locations. And so let's say Foster and Hangtree. That's a pretty good illustration. This dashed line between Foster and Hangtree, and then you draw another boundary that's perpendicular to that line halfway between them. So what we've done is we've created a boundary, and we're saying on the lower left-hand side, all of that area is going to receive the rainfall depth associated with that rain gauge Foster. And then on the other side of the line, it's going to get the depth associated with Hangtree. So we've only got one line. We have to go through all of these. You can see Big Creek and Wyatt. We've got the dividing line between them. And then we have to have a dividing line between Foster and Wyatt, halfway between them and perpendicular to that line. So we've got these series of boundaries, and those are basically associated areas. And then in this table, what we have is for each area, what was the depth and what is the area that that station is assigned to, and it's kind of like a weighted average instead of a simple average. This was just a simple average, 3.26, but when we take into account what's the actual, this Wyatt, that's a lot of rainfall and a relatively large area that we're assigning it to, so that brings the average up quite a lot. And some of these rain gauges that didn't get very much depth, Emmettville, Crystal City, less than an inch, since they're not being counted anymore in this Thiessen method, the average is quite a bit higher. So Thiessen assigns areas based on just dividing lines. Another approach is in the isohyoidal method. You're thinking more about what is the actual precipitation doing. It's not realistic. What this is saying is that on one side of the line there was 9 inches of rain, and on the other side of the line there was 1 inch of rain. And so, you step over the line and it's pouring torrentially, but then you step back again and it's just a light rain. I mean, that's not realistic. So this next isohyetal method says there should be more gradual variations and gradations in the rainfall depth. And so we're trying to create like a series of contours by extrapolating between the known points. So we say, you know, between this gauge where there's 1.04 and where there's 9.10, let's make the divisions more gradual instead of a distinct, discrete, all or nothing approach. So here we're saying, all right, here's the 2 inches, 3, 4, 5, 6, 7. So it's a contour, and you create those contours influenced by the known values. And there are computer programs that can extrapolate and can take them into account. Doing it by hand is really kind of an art to know like what path these contours should take and how far between them to put the contours. But once you have integrated and assigned, you know, you've got your 3-inch band. So what you would do is you'd say all of the area between 3 and 4 inches, I'm going to add up that area amount and multiply it by the average depth between them. So I'd use 3.5 inches as the assigned rainfall depth for whatever the area is between them. And you'd go through and come up with an average that way. So again, now we're back down to 3.31. So ironically, in this particular illustration, our first guess of just using the simple average was closer than the Thiessen method. But it's not always that way. It's generally accepted that Thiessen is better than arithmetic mean, and the isohyetal method is better than Thiessen. And there's a whole lot of other ideas that have been developed over the years, but those are some that I think it's worth being aware of. Any questions about that? Let's see if my job is finished. Complete. All right, great. So now I download the data. Let's go ahead and open it straight away. All right, so we've got the latitude, the longitude, and the date. These precipitation amounts, if I remember correctly, are in millimeters. No, they're in hundredths of millimeters. Better check on that, right? These might be inches. Documentation. Sometimes the data that I've got in the past has been millimeters, and if you wanted to get the actual inches, then you'd have to convert. I guess the best way to know whether it's inches or millimeters is let's sort from largest to smallest, and if it's like in a day 4, then that's probably inches. If it's like 25 or 50 or 75, then that's millimeters. Okay, so I'll sort from largest to smallest. So remember, this is from 76 to 2018. Largest to smallest. Okay, these are inches. So what that means is that the most that we saw during the period of interest was 3.89 inches. Okay, so that's precipitation in inches per day. Ooh, what did I do? And if we wanted to create a, none of this stuff's changing, so I'm just going to delete it. That's all extraneous. But what I will do is insert this rank. So this is the number 1 storm, this is the number 2 storm, the number 3 storm, and so on. So then once you have this rank, what you can also calculate is the return period. And so remember, the formula for return period is the number of years of data that you've got. And that's 42 years. We got 42 years of data. So it's 42 plus 1 divided by our rank number. So 3.89, the return period of that storm is it comes around once every 43 years. But to have a 3.8-inch storm, that has a return period of 21.5 years. So if we want to know the 25-year storm, we would do a linear interpolation between these two values. All right? So that's one of the ways that intensity, duration, frequency tables are generated. They'll also do some statistical massaging by looking at the data tables in adjacent locations, and they'll sometimes get just like an aberration where they know, oh, there happen to be two really big storms that are almost the same depth, 3.89 and 3.8. That was maybe just kind of a statistical anomaly. And so then they make some adjustments. And that's this precipitation data frequency server. NOAA Atlas 14 is what it's based on. And that's the name of a product that is that statistically validated for the entire country calculation of rainfall intensity. All right, so we've been talking about spatial distribution. And spatial distribution is just any kind of representation of how, in this case, rainfall varies over space. So this is for the entire country. Here's the one that we saw before for Hawaii, that it's more rainy on the leeward side than on the windward side. And in a watershed, there can be spatial distribution as well. Temporal distribution is saying, let's look at how the amounts vary over time. So this is a seasonal temporal distribution map. And what this shows is that there's a different pattern of when is the rainy season in Miami, for example, where the rainy season kind of peaks in October, compared to other locations like in Montana, the rainy season peaks in June. So the reason for that is the types of storms that occur. In the Midwest, the dominant storm type is going to be a convective storm, where it's flat, so there's no orography, right? There aren't those physical obstacles that the moist clouds have to get up over, and that's what causes the rain. So we don't have that in the Midwest. So the reason why Chicago, Kansas City, those afternoon thunderstorms you got to be on the lookout for. Your plane will be delayed if you fly through Chicago because of the afternoon thunderstorms. But then other spots, they have fronts that come together. So temporal distribution is just looking at variation in times. And this next figure is the number of days per year that have thunderstorms. And along the coastal parts of the western United States, it's 5 days or less of thunderstorms. Thunderstorms are really uncommon because just the weather patterns or the physical geography isn't there to have a rapid lifting of the moisture. Now, they may have plenty of rain. This isn't just the days with rain, because Seattle, if we had a graph of the number of days of rain, it would probably be like in the 300s or something. Thunderstorms is rapid elevation of that moist air. So what's lifting it really quickly, it's more common in the central part of the United States and down off the Gulf Coast. So temporal means time. People like extreme events, at least in theory. They like examining extreme events. And what they've been talking about is that these storms that are approaching South Carolina and North Carolina may set new records for the amounts of rainfall that has ever been observed in those places. This is a series of figures that looks at all over the world what's kind of like the record storm events that have been observed. So, for instance, what's the 1 hour storm, the most that has ever been seen for an hour storm? Well, there isn't one exactly for an hour, but they saw in Holt, Missouri, a 40-minute storm where they had 10 inches of rain in 40 minutes. Guys, that's a lot. That's really a lot of water. Like, you know how much it takes to cause Fifth Avenue to flood? I mean, we're talking like 2 inches will do it on Fifth Avenue. Less than 2 inches will cause Fifth Avenue to just be a river. So you throw 10 inches in 40 minutes, it's bananas. That's really a lot of water. But, I mean, this is a logarithmic scale, so I'm not sure where in India this is, but they've got a lot of these records. And if we look at how much rain did they have during a 30-day period, in the course of 30 days, like 300 inches of rain. So, like, what's in the United States, the wettest part of the country is like along the Gulf Coast, down in Houston or Miami. And, I guess that's not true. Hawaii, like the mountains of Hawaii probably has more. But like in the continental 48, like it's really wet if you're getting 50 inches per year. And these guys saw in a month 300 inches per year. So that's plenty of rain. It'll be interesting to see where on this scale maximum precipitation, like the 40 inches that they say they're going to get down on the coast of South Carolina. So if that's 40 inches in a day, a single day, that's about right. Smithport, Pennsylvania, in 6 hours, they saw 30 inches. So, and I'm surprised to see that because Texas makes sense because you'd think it's maybe a hurricane. But then here's one for West Virginia, Rockport. Anybody know where that is? I've never heard of it. All right. The interesting thing is that it follows a linear scale. That, there's more or less a slope to this line that can be reproduced. You can find the rainfall depth in millimeters by 425 times d, where d is the duration in hours, to the 0.47 scale, 0.47 power. This has all been from observation. Sometimes they'll even take it a step further, and they will extrapolate based on the capacity of air to hold water and what range of elevations you're likely to see holding on to water that could precipitate. And so sometimes, like in a dam break simulation, they'll consider what if the dam was full and we saw the probable maximum precipitation for this area, meaning you've got all these storms colliding and physically the absolute most water that could fall out of the sky. Because the consequences of a dam failure are so extreme that they have to consider the worst case scenario. Like we're not talking about 2-year storm or 100-year storm. They're talking about like the 10,000-year storm in the analysis of dam performance. And so part of that analysis is looking at the probable maximum precipitation. And here are some tables. There's a publication, HMR 41, and I'm sure it's been revised since 1960, but this is a figure that's in your textbook that's showing for a certain watershed area what you could expect the rainfall amounts to be based on how long the storm was. And so, for instance, if you have a relatively small watershed and a 6-hour storm, for a 10-mile square watershed, over that average of the 10 miles, you may see 24 inches of rain in 6 hours as a probable maximum in the United States. Why do you suppose, if you're talking about a larger area, so instead of 10 miles, 1,000 square miles, why is the amount lower? That's right. Just think about the odds. The odds are that if you have a lot of rainfall, that it's just in one spot you're seeing that concentrated intensity. It's less common to have really intense, heavy rainfall over a big area. So, there may have been that center cell that was dumping loads and loads of water, but it was probably moving around. And so if we're talking about 1,000 square miles, probably only part of that watershed had the really intense stuff, but then the rest of it had lower intensity, and so the average over the 1,000 was a lower amount. So that's the trend that I want to show you. First of all, that the duration, as the duration increases, we're not doubling the amount. If you go from 6 to 12, for a 10 square mile watershed, we go from 24 to 29. So we're not doubling it, and it's for the same reason. You can only have really high intensity for a short period. And so by doubling the duration, the intensity went down, although the absolute amount is marginally greater. So those are the general trends that you should be able to discuss, the concepts here. is that as the area that we're considering increases, like the entire Mississippi River Basin, you're not going to have a storm that's raining on the entire, like 38 states of the Mississippi River Basin all at once. It's only part of that watershed that's receiving rainfall at any given time. And so if you're considering a 10,000 square mile area, then maybe the maximum you could expect to see over that entire area would be 1.7 inches of rain in a 6-hour period. So those are the general trends associated with maximum precipitation. This is a graph that kind of shows just a statistical technique that can be used to generate your own data. You know, this table is for just a discrete number of hours and a discrete number of a watershed area. This function, which is in your text, shows you how you could find out as the watershed gets bigger, how the percent of rainfall, maximum rainfall you'd see at a single point is averaged out to that larger area. And as the shorter duration it is, then you may have more variation between a single point and the entire area than if you have a long duration storm. There's going to be less variation between the point and the entire area. We won't go through the calculations of this. It's not unimportant, but it's really the trends that we've already talked about that's at the heart of it. But this is important, and this will come back several times through the semester, especially when we're doing watershed modeling using WMS. Man, it's just getting colder and colder in here, isn't it? Boy, oh boy. I feel like I'm at Ski Dubai. That's the indoor ski resort, you know. Here, I'll cool it off. It's cooler. All right. Different regions have different kind of temporal distributions. So along the coast, they don't have very many thunderstorms there. Along the coast, it's that kind of like slow, gradual storm that happens all day as a drizzle. So here you see on this graph, type 1 and type 1A are the least steep of all of them. Type 2 is the most steep, and like the slope of the line is a representation of intensity. So this graph is saying with time on the horizontal axis and the percent of a 24-hour storm on the vertical axis, at the end of a 24-hour cycle, you've had 100% of the rain. But really the key thing is you don't assume that it's all coming in an even amount during that 24-hour period. You're going to have a little bit of rainfall at first, but then the typical pattern is that the rainfall will increase during some middle portion of the storm. There will be a really high intensity, and then it'll taper off again. So we have type 2. All of West Virginia experiences type 2 typical behavior of the most intense rainfall compared to these more coastal areas. And type 3 is where it's influenced by hurricanes and like storms from out at sea. And we don't really have those in West Virginia, but these are all basically the places they get hurricanes occasionally. So there is this figure that shows these values, and we also have, when we get into watershed modeling, it's been digitized. And so if we say there's a 3-inch storm that happens during 24 hours, this figure would tell us how much intensity there is during that 24-hour storm. So you could take a depth and then plug it into this, and it will tell you the intensity at all times during the duration. So here's that figure where if you knew the rainfall amount, then you could multiply it by the fraction, and that would tell you how much of the depth has occurred up to a given time. And it varies by type. And what you need to remember is that we are type 2 here in West Virginia. This is taken from your textbook. This Hydro 35 was the precursor to NOAA Atlas 14. So The NOAA Atlas 14 is the precipitation data frequency server where we were clicking at a location and it told us the IDF curve. The reason they were able to do that is that in the years prior to it, they generated these actual physical maps where this map is how much depth you can expect to see for a 2-year, 60-minute duration storm. And so if you click on the spot, well, you don't click, you look with your finger and you find the contour line. It looks like this is the 1.4-inch contour, and here's the 1.2, so we'd be 1.25 inches here in the tri-state. 1.25 inches is the 2-year, 60-minute precipitation depth. And then you'd look up another paper map that would show you the 100-year, 60-minute. And then what you'd do is you would yourself interpolate between the 2 and the 100 to find other return periods. And so here's the formulas. They're also in your textbook that says if you have, for instance, the 5-minute storm duration and you have the 15-minute storm duration, you could calculate the 10 by just doing kind of a weighted average between them. And the same thing, you will be given the 15 and the 60 to find the 35 with this weighted average. And then there's another way of interpolating for return periods. And so these were duration interpolations, but you also interpolate by knowing the 2-year storm and the 100-year storm, which you look up off of the map. You would find, if they're asking you about Chicago, you'd have to know where Chicago is. It's right there. There's Chicago. So you'd look it up. You'd say, I know what the 2-year is. I know what the 100-year is. And then I'm going to use this formula and the value coefficients for A and B to interpolate and tell me the 5, 10, 25, 50. And the reason why we're able to do that is that across the country, there's roughly the same pattern in what an IDF table looks like. I mean, if you know the green line, which is the 2-year storm, I guess the yellow line is the 2-year storm. If you know the 2-year storm and you know the 100-year storm, then the rest of them are just kind of like in between at a pretty regular interval. And that's what this formula does, is it's just saying once you know the 2 and the 100, there isn't that much irregularity that can't be predicted with just this weighted average. So I think you may have a question on this homework that's due a week from today where you have to plug numbers into this formula and into this one based on values you got from the paper map, which is in your book. Any questions so far? So we're talking about rainfall, and sometimes it is confusing to make the jump between rainfall depth and rainfall volume. So when they talk about how there may be up to 40 inches of rain, that's going to happen on some parts of the coast of North and South Carolina. So let's say 40 inches. So that's just one dimension. How do we turn it from 40 inches of rain into cubic feet? Well, that's where you're looking at the area that it fell over. So here, the rainfall amount can either be expressed in terms of a length or in terms of a volume, and the difference is that you'd have to multiply by the area. Rainfall intensity and rainfall amount likewise have different units. The rate or intensity is going to be length per time, whereas the rainfall amount is most typically just described as the depth that was encountered. And sometimes that will be that they put a ruler into a container and they actually measured the depth, but usually more often it's going to be the tipping bucket that they're using as a way of measuring the rainfall. A lot of the IDF tables we've seen so far today have shown return period, which is also called recurrence interval. And that is a statistical average of how much time is between storms of that duration. And what sometimes throws people off is when you can say, oh, we had a 100-year storm. It doesn't mean it's going to be 100 years until the next time you see a 100-year storm. It might be 200 years, or it might be 6 months before you have another 100-year storm. It would maybe be a little bit more accurate if we referred to those storms in terms of their probability. And so a 100-year storm in any given year has an average probability of 1%. But some people are really lucky and some people are really unlucky. So you can have improbable events happen in sequence, and that's what's sometimes hard to keep in mind. So I told you it's pretty rare to have stations with really high resolution, like 15-minute data. This is a map that shows for when they were making the NOAA Atlas 14, that precipitation data frequency server. These are the stations that went into that, because these are the stations where they had a relatively large amount of data available. And the graph that's in the lower right shows how much time is in that data. So how many of the stations had how many years of data? You know, there's only one station, I think, that has 110 years worth of data. There were 10 stations that had 100 years worth of data. But something happened 60 years ago where it looks like they added a lot more stations more frequently back then. And so this is for daily. This is the daily data, where they just have the 24-hour totals. It seems like a lot until you're interested in a location that's kind of remote in between spots. Here's the stations where they have data that's available either on an hourly basis or anything more frequently than hourly basis. And so now this is really thinning out the herd. In each state, in West Virginia, there's maybe 15 stations where hourly data is available, in most cases at airports. All right, so is this rainfall depth or rainfall intensity that we're looking at? Depth, that's right. Because if it was intensity, you'd have the most for the short duration. So this is amount. So if we have increasing duration and increasing amount, then that tells us that it's amount rather than intensity. All right, so just to emphasize on spatial distribution, the relationship between spatial distribution and geography. Like for West Virginia specifically, why is there more rain on the east side of the state than where we live in the west part of the state? Mountains, altitude, orography, exactly right. And I remember I went to Richwood a couple of years ago for the first time. It was in October, and I guess that's right about here, like in the Cranberry Wilderness area. I was blown away at how different it is there. Like the types of plants that you see, totally different from, I mean, it makes Cabell County look like a barren desert. Like I felt like I was back in Nevada when I drove home after having spent time like walking through ferns. It was like a rainforest, literally like a rainforest. It was the forest and it was raining, and it's a high rainfall area. It's 60 inches a year compared to like in the 30s. So it's really beautiful out there. If you've never been out to like Richwood and Cranberry area, I really encourage you to check it out sometime. All right, that's it for today. We'll wrap it up a couple minutes early. You do have as much as I'm going to give you to get started on some of those problems for the homework. Of course, in this class, you're kind of getting close to the grad school approach where you're kind of on your own, reading the book for some of the ideas, not getting as much stuff directly spoon-fed to you, a little more independent learning since you're getting closer to graduation. So you definitely should, I hope, be keeping up in the reading. The schedule that I gave you at the beginning of the semester shows like which textbook chapter we're in as we go through each lecture. So, you know, doing the reading will keep you ready for the quizzes and help you understand the material a little bit better. So I'll see you on Tuesday.